Okay, well, where did we stop? We have to hurry up now. Where did we stop? Where, I don't know where we stopped. We stopped here. Okay, so I was reviewing very quickly rotational kinematics. And here you compare the linear motion and the rotational motion, and I try to do it in a nutshell. So here you have the connection between them. So if you have something here spinning, okay, so that will be the linear speed at a given point from the axis of rotation. So it depends how far from the center you are. You multiply by 2 here the location from the center. The linear speed will be multiplied by 2 because you are covering more distance during the same time, but the rate of spin will be the same. So you have these relationships. So those relationships are only in magnitude. So that will be the arc length. That will be the angular displacement. So we did that last time. That will be the linear speed. That will be the angular spin. So that means the rate of spin. And then here you have the linear acceleration, but it's the tangential acceleration, is the tangent component. And that will be the angular acceleration. Is that clear? So one thing, so this is in magnitude. So I brought this, okay? Appreciate, it's very heavy. So you see, I'm gonna apply a torque. So you're gonna see when you apply a torque, it's like a twist. So it's gonna start spinning. Now the angular speed is a vector. So you're gonna take your right hand like this. If it's spinning this way, the vector will be this way, right? So that will be your vector rotational speed. If I rotate this way, that will be your vector going in this direction. So you use your right hand. If I apply a torque and I make it go faster, the acceleration, the rotational acceleration is a vector, and it's going to be also in this direction because it's going to pull on the initial velocity to make it larger in magnitude. If I apply a torque to make it go slower, so then the acceleration is in the opposite direction relative to the rotational velocity, so it make it go slower. Is that clear? Yes, you have to, it's called the right hand rule. I'm getting tired. So the other thing you can do, okay, it doesn't have to spin faster or slower. You can apply a torque like this just to change the direction of the velocity. Okay? So that's what you are doing when you are on your bike. For example, okay, motorcycle, you apply counter steering, so you push here on the left and you are changing the direction. My arms, yes? So it's not that obvious. Okay, and then here you see the connection. Let's say that will be the angular displacement. Okay, so you have the average angular speed is the angular displacement divided by the time, like the average speed is the distance, so linear distance. I'm not talking about displacement. Displacement is a vector. The average speed is the distance over time. And then you have all the kinematic equation that you already know, all those equations here, and you have exactly the same equation, but for rotational motion. Okay, so again, this is not that obvious. If something is rotating here, you use your right hand. That will be a vector. The notation is omega. The magnitude is rad per second. Okay, so if you spin this way, again your right hand, the vector will be down, and if you spin that way, the vector will be in this direction. So it's a vector. Okay, so just a parenthesis here. When we talk about this relationship between how fast it's spinning faster and how fast it's moving faster, right? That relationship between the two accelerations is between the angular acceleration and the tangential acceleration. So remember from previous unit, here, let's say you are holding an airplane, a toy, and it's gonna go around a circle here. You see the tangent, the acceleration has two components. One is tangential that will make it's like the thrust, right? It's the same direction as the thrust, so it's gonna push the airplane to go faster. But this acceleration here is a centripetal acceleration that will keep the airplane on track. That acceleration here is always perpendicular to the velocity. So when you have this relationship here, right, it's only between the angular acceleration, how fast it's spinning faster, and the tangential acceleration. For the centripetal acceleration, then you have to use this equation to remember from last unit, v squared over r. V is r omega, so you get this relationship. When you want to connect linear kinematics and rotational or angular kinematics. Okay? Any question? Okay, so we get to the torque. So torque is like a twist. The notation is tau. Okay, so torque is a way, it's a physical quantity, and it's a vector. It's a vector. It's a physical quantity that will measure how efficient is a force in applying a twist. So in making it go faster, spin faster, slower, or change the direction of the spin. Okay, so that will be a torque. So let's find out what should be inside that torque. The force, does it matter? If I apply a little force or a big force, does it matter? Yes, right? Larger the force, more spinning you get. So the torque should have inside the force that you are applying. And then the location of the torque, does it matter? The force, right? If I spin here, will it be easier than if I start to spin there? Yes, right? So it's like a door. If you want to open the door, there is a reason why the knob is far away from the hinge, the axis of rotation. Farther away, easier. That means more efficient. That means larger is the torque. So the torque should be force, okay, times the distance between where you are applying the force and the axis of rotation. So in engineering, or physics, or anywhere, when you have an equation, you multiply or you divide depending on the dependence. So it depends on the force. I'm going to multiply force times distance. And then is the direction matters? Like if I want to spin and I push, is it spinning? No, I'm getting tired, right? But it doesn't spin. So the direction matters too. So I need some trick, right? So the most efficient will be when the force is perpendicular. So a force is a vector, so it comes in two components. So I need to use the perpendicular component. And that will be the definition of a torque. So that will be the force times the distance between the axis of rotation and where you're applying the force and the direction. The force has to be the perpendicular component. Okay, so something very simple. Obviously, larger or longer is the range, easier it gets. There is always a trade-off because there is no free lunch. If you want the bolt to go a tiny bit, you have to apply a large, to apply the force over a large distance. So there is a trade-off between the force you apply and the distance through which you are applying it. Okay, so, but anyway, the torque will be, in that case, force times distance. So it's easy, right? So, for example, if you divide the distance by 2, you apply the same force, what's going to happen to the torque? Ah, very good. It's going to be divided by 2 because you have the force, you have the distance, and you have the direction. Okay, so the nice thing about that is that you won't have to go like zoom and zoom. Okay, it's just a little twist. But of course, you need more muscles, right? So I don't know, there is a video, but since everything is all over the place, I don't know if I can find the video. Okay, so for example, in that case, so because it's a trade-off, between the force that you apply and the speed. Distance is speed, okay, because it's the time. Speed is distance over time. So you see here in that case, so he's trying to make it fly. The kids will fly, right? Because they experience a centrifugal force. But you see, he's pushing very far. By pushing very far from the center, okay, it will be easier. But you are not going to go fast. So if he wants them to go fast, he has to go close. So it depends what you want, right? So if he's gonna push here, right, of course it will have more force applied. He has to apply more force, but he will get more distance, which is faster, right? And then it can be fun.
Great show, however, just fascinating as that realization was, I also discovered that they put hemostatic.
Okay, so that's cool. So it's a trade-off, right, between distance and force, or force and speed. So in that case, where do you want to push to make it more efficient? C, right? You're going to increase the torque. It's going to multiply your effort. So this is called mechanical advantage. So if the ratio here between this and that, so this is the load, this is the effort. So if the ratio is 4, so 1 and 1, 2, 3, no, that is 3, 1, 2, 3, and here it's 1, the mechanical advantage is 3. Make you 3 times stronger. So if you can lift only 20 pounds, all of a sudden you can lift 60 pounds. But the price to pay is that you have to push here over 6 times the distance. Okay, so in those cases, the distance is the same. Which one will be more efficient? So more torque, larger torque. See, you push the stick into the ground. A, perpendicular is the most efficient. If it's not perpendicular, then you have to find the components and find the component, the perpendicular component, to do the math. Yeah, so you have to find the perpendicular components. So you go from the tail to the head. So you go down and then this. You have to find that component here using trigonometry. We're going to do that. But anyway, here is an example. So what's the torque here applied? 0. You are not efficient. All you are doing something. You are causing something, right? You are causing the door to go into the hinge. Okay, it will accelerate a tiny bit, but you are not causing a rotation. So there is no twist. So the torque is 0, not the force. In that case, you are 100% efficient. Like it's the best, the largest torque that you can get with the same force and the distance. And in this case, you have to find the perpendicular component. So you have 3 ways to do it. You have 3 ways to find torques. So in that case, I can say, okay, force is a vector. It comes into components. Each component has a different job, right? So in that case, it has a perpendicular component, and here it has a parallel component. So this is perpendicular to that, and then this is perpendicular to this, so that will be 30 degrees. So this is 30 degrees. Remember from geometry, if you have an angle here, and this is perpendicular, and this is perpendicular, okay. So that will be the perpendicular, and let's say that will be the distance. That will be the distance. I'm going to call that d, between the axis of rotation and where you are applying the force. The torque will be the perpendicular component times d. So sometimes it's cosine, sometimes it's sine, depends. You can use the trick, right? If you go from the positive x-axis, the y component is always sine, but that will be sine 60. So it will be f cosine 30 times d in magnitude, okay? And then we're going to decide that if you are trying to make counterclockwise, the torque will be positive. If it's clockwise, the torque will be negative. Are you with me? And then torque is a vector, so you're going to take your right hand again. If you are trying to make this rotation, like here, you are trying to make this rotation like this, do you agree? So the vector torque is towards you, out of the screen. You try to open the door to make it twist this way, the torque is towards you. Okay? Torque is a vector. The torque is something that will pull on your velocity, angular velocity, to make it spin faster or slower or change the direction. So the torque, I'm going to do this, is coming towards you. Agree? Now there is another definition that you can use. It's used more in engineering. It's called the lever arm. So it works also. So the other definition, you have 3. The most important are this one. And then you have the third one using vector calculus. But the other definition will be the force. And instead of having a perpendicular here, I'm going to have a perpendicular here. So this here, it's called the perpendicular distance. And this is also called the lever arm. So it's important in mechanical engineering. So how do we find the lever arm? You take your force, and this line here is called the line of action. So you extend it. And then you take the axis of rotation here, and you take the perpendicular distance. So this is called the perpendicular distance, or the lever arm. And if you do this one, you see that cosine 30 equals adjacent over hypotenuse. So the lever arm equals d cosine 30. So the torque will be F d cosine 30. And you get the same thing. So it depends on the problem. Easier will be to find a perpendicular, but we're going to see a problem, typical problem of static equilibrium, where sometimes it's easier to find the lever arm. So it's in geometry, right? When you have a point here, yeah, you can find different distance, but the perpendicular distance is the one that you project here, and it's perpendicular. That will be perpendicular distance. So you can use this, you can use that, or you can use vector calculus. Okay, and but for this class, this one or that one will be fine. Just to because most of you will have to take vector calculus, so in that case you can use a vector and you use the cross product. So it will be the distance as a vector cross f. Okay, so you can dot vectors or you can cross vectors. So this is called a cross product. I invite you to go back to unit 1 of your textbook. So that will be the vector distance. In that case, will go from here to there, right? So that will be your vector distance. And the cross product, the magnitude, will be d times f. And for the dot product, we have a cosine. The cross product, we have a sine. That will be the vector, the angle. And you will get the same thing. Because instead of having 30 degrees, you're going to have the complement. See? Hmm? What? Sine, yes, you can say, yeah, yes, sine 60. So it will be the same. Okay, so I'm going to give you the formal definition, but just to give you an idea. So for this class, you just have to worry for this one, and that will be for more advanced, right? I'm still going to talk about it, but for the problems, you use this or that. It's not that hard. Okay, so what's the cross product? You have different way to torture your hand. If you are crossing vector A and vector B, you can take your right hand. You all have a right hand. Yes, that will be vector A. That will be vector B. And that will be vector C. Okay, so this is C. The vector C is A cross B. So when you cross two vectors, you get a third vector. The magnitude will be magnitude of A, magnitude of B, sine the angle between A and B, which is just the area. This is the area of that parallelogram here. So when you dot, you use cosine. When you cross, you get sine. Cross, you get a scalar. Cross, you get a vector. You can also use components here, like we did for the dot, and you can use a matrix. The other way to do cross, you go A, B, C. A, B, C. So it's a right-hand rule. A, B, C. You go from A, you fold toward B, and you get C. Maybe this way is easier when we are doing torque. So anyway, again, let's go back to the three definitions. This is a door. Imagine this is a door. This is the hinge, the axis of rotation. That will be the distance to where you're applying the force. You apply a force this way. One easy way to do it is to say, okay, it will be R times the perpendicular component, which in that case you're going to use a sine. So it will be F sine theta times R. Or you can use the lever arm. So in that case, you're going to extend this. Okay, you are extending. This is called the action, the line of action. And you will find the perpendicular distance. So you will say F times the perpendicular distance. Or you are using the cross product. So anyway, if the force you are applying is trying to rotate the system this way, the torque is going to go that way. And torque will be proportional to your acceleration. If there is a torque, there is a spinning faster, slower, changing the orientation. Okay? So again, I'm taking an example here again. So here you need to find the component here, the perpendicular component. So you can say, okay, the torque will be 10 times the force. I don't know how much is the force. Times, in that case, it will be the cosine 40 degrees. It's a cosine here. That's one way. Or, again, you extend the force. You take the perpendicular distance, lever arm. So you will say 10 cosine 40 times F. Or you take the definition of the cross product. You say, okay, the torque will be F times here. F times R times the sine between F and R. And these are vector. You see, if I want to find the angle between this one and that one, I have to attach them by their tails. Okay, remember how to find the angle between vectors, right? I have to take this one and then I paste this one here. They are attached by their tail, and then I can find this angle here. That angle here will be 40 plus 90. It will be the sine of that, which is the same as cosine 40, because the angles are complementary, so you get the same thing. Okay? If the torque is counterclockwise, we're going to say it's positive. If it's clockwise, we're going to say it's negative. It's a vector. So in that case, take your right hand. It wants to twist this way. So the torque will be in the board. See, twist this way in the board. So you make a cross. Yes? Are you with me? So here it comes from a website. It's called Hyperphysics, and it's a very, very nice website. And they cover all the physics, so it's very good for engineer. Hyperphysics, it's free. So anyway, this is the axis of rotation. That will be the distance to where you're applying the force, right? So there is a torque. You are making it going faster, spinning faster. The thumb show you where is the torque, the direction. Okay? If you do a cross product, you take your free finger, you say the distance is here, the force is in this direction into the screen, so that will be your torque. A, B, C. Or you can say A, B, C. Into the board, towards you. Remember, a vector is like an arrow. Okay? So again, rotational kinematics, rotational dynamics in a nutshell, as an introduction. So linear motion, you have the mass. The mass is resistance to the change in velocity, right? So you can apply the same force to different masses, you won't get the same acceleration. Now, for rotation, it's more complicated. It's not only the mass, but it's also how far the mass is from the axis of rotation. So with a bike, you see, that's why here it's empty, and all the mass is here. Okay, so you have more inertia, so it's harder to fall because of conservation of momentum. So inertia, when it comes to spinning, not only depends on the mass, but how far the masses are from the axis of rotation. So for a demo, if you know how to do it, or you can go to ice rink, you take masses into your hand, like 5 pounds, 5 pounds. You spin. What's going to happen if you bring the arms in? Spin faster. You lower the inertia. So inertia depends not only on the mass, the 10 pound and the mass. I mean, not here, but the mass of the arms, but how far the masses are from the axis of rotation square. So the inertia will depend mass times distance square. So it depends on the distribution of the masses about the axis of rotation. So that's why in a bike, all the weight here of the wheel is on the edge. Increase inertia. So here, remember, told you acceleration is just a force per unit mass. Or force equals ma. Same thing here. Torque equals inertia times acceleration. If it's spinning faster, slower, or change the direction, it means there is a torque applied, but how much acceleration you get depends on inertia. It's not the same consequence. And then you have momentum, linear momentum. If there is a change in momentum, you have a kick, impulse. Same thing here. You have a spin. It's called angular momentum, angular spin. Okay, so if something is spinning, it wants to keep spinning. Okay, it's not happy. Like if you want to stop it from spinning, you need to apply a force. So it has angular momentum, and it increases stability because once it has momentum, it doesn't want to lose its momentum. So, for example, if you shoot a bullet, they do it in such a way that it will spin like this, right? To make sure it will be very stable because it has momentum. If you want to change that momentum, you need to apply a big torque. And then you have work. Work is how much energy is transferred. You need to apply a force over a distance. So same thing here, you can transfer energy to this wheel. So sometimes it's called a flywheel, right? You can store energy, you can store kinetic energy. In a wheel, it's called a flywheel. So I'm storing kinetic energy and then I can get it back. They do that with generator, I think. So anyway, if there is work, okay, there is a change in kinetic energy and you are storing kinetic energy. So that will be the torque times the angle. Kinetic energy 1/2 mv squared. Kinetic energy same idea. Power force times speed. Power torque times speed. Which means if you are doing biking, you have the gears and there is a trade-off between the torque and the speed. If it's easier, if you go up slope, you change the gears, low gears, but you are not going to go really fast. So again, nutshell, spinning, that will be your velocity. You take your right hand this way. If you apply a torque to make it go faster, okay, it's like pulling on that velocity to make it larger, and it's going to spin faster. If it's spinning and you slow it down, now the torque is going to be in the opposite direction. The acceleration is going to be in the opposite direction. So it's going to shrink, right? The magnitude is going to shrink. Or that's the very weird stuff in physics. It's called the gyroscope effect. Very weird. It means when something is spinning, you can apply a torque to change the direction. I apply a torque to change the direction of spin. So in that case, it will be perpendicular and very weird things happen, right? If you do counter steering, like if you push in this direction, I'm applying a torque and all of a sudden the wheel will do something like this. Try with your bike. It's scary because if you do it with your bike, you push, just push this way and all of a sudden the bike is going to do that. I tried and almost failed. So they do it usually with the when they are racing. Okay, so again, if something is spinning, okay, it has momentum, you can change the direction of spin. Okay, so let's go back to torque. What will be the torque applied by the force F1? 0. Okay, do you all agree? The torque applied by F2, what do you multiply? So, okay, so it will be sine 30 times 20. Yes. And times 1. Times 1. Do you all agree? Okay, you multiply 1 times 20 times sine 30, which is sine 30 is 0.5. So it's going to be 10. Is that right? 10 times 1. So it will be 10 Newton meters. The unit is Newton meters. Agree? Yes. No, it's a force times a distance. So it's a Newton times meters. Because it's not a force, it's a twist. It's how efficient you are in making the rotation happen. Torque is a twist. So, for example, if you and it says so we are doing chapter 10, right? So in that case, the torque applied by F2 about, so you have to use your axis of rotation. So because the torque won't be the same depending on the axis of rotation. And sometimes you are the one who decide where is your axis of rotation. It's always relative to. It's not like a force. A force is not relative to. A force is a force. A torque is applied by a force relative to this axis of rotation. You can call that the fulcrum, but sometimes it doesn't make sense. You have to decide where. So that will be, okay, the force, okay, but it's the perpendicular component, so it's going to be a sine 30, okay, and the distance is times 2. The unit is Newton meters. And then you take your right hand and you see this force, you look only at this. This force wants to make it rotate in this direction. So that will be counterclockwise. So it means it's going to be positive. And then you take your hand. So this way, the thumb is towards you. So the vector torque will be towards you. It's a vector. This is just a magnitude. Okay? This one, I will say the torque applied by F1 relative to the axis of rotation, it's going to be 8 times 5, okay, and Newton meters, but it's clockwise, so we have a negative. It's a negative here, and that will be into the board, into the board, into the board. Yes. Which rotation? That if you have a vector, this is a vector, right? If the vector goes into the ball, then you see a cross because it's like an arrow. It's the tail of an arrow. No, because it has, okay, the negative and positive, it's going to be helpful when we're going to do equilibrium. But sometimes it doesn't have to be, of course, you're right. So it could be positive or negative. That's a good point, right? But sometimes it could be in 2D. So in that case, it doesn't really help. Okay, so in addition to positive and negative, you need to know the direction. So in these cases, because it's in one plane, it doesn't matter. Then it will be covered by positive or negative, but it still have a direction. Yes. So if it's counterclockwise towards you, clockwise into the board. They do it this way because it's like this. See? So you see a cross. It's the tail. Okay, so here you have some example. Maybe I'm not going to do all of them. So that will be the torque. What will be the torque here? 0, right? So that will be 0. That will be the most efficient. Farther you are, most efficient it is. So if you want to do this one, for example, 2 meter, I guess it's at the center. It has a perpendicular, parallel, or you can take the perpendicular here, right? Only this one is doing the work. And that will be a sine. It's a sine. Sine or cosine 30. Okay, so the torque applied by F relative to 0 will be the force times 2, if this is 2 here, times sine 60 Newton meters. So this is clockwise or counterclockwise? Clockwise. So it will be negative. So into. Okay? So in that case, the largest torque relative to this axis of rotation will be 3. Very good, right? Because you are farther away. It seems like it's your guts. Guts talk to you. You know, there is a connection between the guts and your brain. Your guts knows physics, so it says to your brain, number 3. Under, like here? Yes. So here, just talking about rotation. Okay, so a lot of application in biomechanics. So in that case, so that comes from an algebra class. So this is the muscles. This is your axis of rotation. And sometimes it's easier to take the lever arm, but you can do the perpendicular one. So let's do the lever arm for a change. So you extend F. That will be your axis of rotation. So you take the perpendicular distance. Okay, so we are not going to use this one, but you can use that one too. But we're going to do the lever arm. So you see, it's not the whole muscle that will lift you. It will only be some component. So I'm going to put the axis of rotation here. So your muscle, I don't know even, is it a muscle or a tendon? Oh, it's a tendon. Oh, yes, I was right. Okay, it's a tendon. Um, yeah, because tendon are attached to muscle. Trying to remember that. Okay, so it will be, um, so you extend, that will be the perpendicular distance. Okay, so you see that the perpendicular distance is the lower arm, and that will be the distance here, cosine. Okay, so it will be 3.6 times 10 to the negative 2 cosine 55. Do you agree? So it will be 790 times 3.6 times 10 to negative 2 cosine 55 Newton meters, and that will be clockwise. So it will be a negative, so it will go into the board. This is the magnitude. Okay, now you can do it a different way. You can get the perpendicular instead, and you will get the same thing. It will be also a sine of 35, so it will be the complementary. Any question? So the answer is 50 Newton meters. So it's for people going into oh, I just had a student who applying for a doctorate in physical therapy. I think it's a great career because with all the people on computers, that's how we're gonna end up. So what's happening here as you get older, if you don't go to the gym, if you don't exercise every day, gravity is winning, and you get stuck in this position. So look at the upper body here. So what's going to happen? You have gravity, because gravity is always the winner, right? At the end, gravity. So the weight of the upper body is going to go straight down. Do you agree? So if the body doesn't want to collapse, what is that? What do you think this is? From from the back, right? The upper back muscle has to be applied all the times, and that gives you very bad back pain because you see you have a torque, so you need a counter torque. You need an equilibrium if you don't want to fall. So that triggers a lot of back pain. So this is to explain. It's not actually I found that on the internet, but it's to explain difference between men and women. So women have obviously larger hip. That's for babies, right? Men narrower hip. So what it's gonna mean? It means that women tend to injure their knees more than men because you see here, if this is the axis of rotation, you know because of gravity, it's easier to apply a torque about the axis of rotation, so it's easier to damage. For men, you see, it's straight down, so usually they don't have issues so much with their knees. It's like a women thing. Okay, so if you look at anatomy, many things can be explained um, with biomechanics. Okay, so that's easy. So static equilibrium, big deal. I will tell you what you're gonna have for the final. Big deal for civil engineering. Because if you want a static equilibrium, you need the net force to be zero, but you also need the net torque to be zero. So if you have a torque, you need a counter torque. So it's in equilibrium. So we have a lot of static equilibrium. So this is called static equilibrium. So not only you want the sum of the forces to be equal to zero, you want the sum of the torque to be equal to zero. So that means no twist and no motion, like no acceleration along the linear motion, right? So Here it's easier because you don't have, actually you do have components, but anyway, here you have the sum, the x component equals 0, the sum of the y component equals 0, and here you have the sum of all the torques to be equals to 0. Okay, let's do something very easy that you can do with your guts without taking physics. So you see here, it's an equilibrium. So this is called the fulcrum. So here the mass is 1 kilogram and that distance is 10 centimeter. This is 1 kilogram, so 2 pounds, and this is 1 pound, so this is 500 grams, so half the mass. What's going to happen to this distance here? It's going to be double. Yes, double, right? If this is 1 kilogram and this is half, if this is 10 centimeters, that will have to be 20 centimeters. Okay, it's an easy static equilibrium. This torque, okay, wants to make it clockwise. This torque wants to make it counterclockwise. If I take my hand, this torque clockwise goes into the screen, and this torque goes out of the screen. So you see, why is it a vector? Because the two torques are going to kill each other out. One coming toward you, one coming away from you. So they're going to balance out. Torques are vectors. Okay? So I'm going to write the sum of all the clockwise torque equals the sum of the counterclockwise torque. So if I do it this way, I don't put the positive or negative for equilibrium. So remember, it's like we did everything up equals everything down, everything right equals everything left. Either you have the negative and you just say the sum of all the torque equals 0, or you don't put the negative and you do it this way. So I'm going to say F2 times D2 equals F1 times D1. And this is static equilibrium. Because you have an equal sign, you don't need to convert distance or force as long as it's the same unit on both sides. Only when you have an equilibrium. If you are asked to find the torque, so then you need Newton and meters. In that case, you can just keep kilogram. So this is 1 kilogram times 10. I keep centimeters because I will have centimeters here, equals 0.5 times 20. Because if I want to convert to meters, I divide by 100 one side and I divide by 100 on the other side. Okay, because it's like an equality, right? It's like a scale. So if I divide by 100 here, I divide by 100 here. So if you have centimeters here, you can have centimeters there. Yes? That was my other class, and usually it's Halloween when I get to here. So we are past Halloween, but it's with my other class, so it's fine. Okay, can you answer this one? It is super easy. Okay, 3 Newton, the 5 Newton is placed 20 centimeters. So this is 20 centimeters, and this is question mark. So that will be clockwise, that will be counterclockwise. So the sum of the clockwise equals the sum of the counterclockwise. So clockwise will be 5 times 20 equals 3. So that will be 3. Yay! Is that right? 5, yes, right? So the distance will be 5 times 20 divided by 3, right? Centimeters. $33. Any question? No, that's what I said. When you have a static equilibrium only, then you don't need to worry about converting as long as you have the same unit on both sides. Only when you have a static equilibrium, because if you convert to meters, you divide by 100 on one side, you're going to divide by 100 on the other side, so it doesn't matter. Right? Oh, okay. So yes, that's thank you. Yes, so that's a very good point. Thank you. So in that case, for number A, yes, you are right. So for number A, I will say the torque applied by the 5 Newton relative to the fulcrum will be 5 times 0.02. So in that case, you're right. So it will be 0.1, 0.2. So that will be 1 Newton meter. So in that case, yes, you have to convert. Yes. But when you do equilibrium, no. Depends what they want. Okay, so let's no. Uh, I don't know. This one is easy. We're gonna have assignment. I want to get to the one that will be on the final. Okay, this is a demo that I did. I'm 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 gonna remove the sound. I don't like my voice. Okay, you see? Sometimes it's hard. I'm sure you did it. Did you do it during the lab? You didn't do. Okay, so that's a why not? You know, you can have a demo like this. Sometimes it's hard to get the equilibrium, but that means that mass times this distance equals this mass times that distance, right? You see, when you are French and doing physics, right? This is Napoleon and De Gaulle, who is very famous too. And you can do more. Okay, you can do something like this. So in that case, you will have M1 D1 plus M2 D2. So that will be the sum of the clockwise torque equals M1 D1. Okay? Lost. Okay, so you have this is this is counterclockwise, yes. So counterclockwise equals the sum of the clockwise. So this is M1 D1 M2 D2 M3 D3. Okay, so you're gonna have M1 D1 equals M2 D2 plus M3 D3. And we can use that usually to find unknown mass. Okay, that's in the antique time, antiquity, you know, the antiquity, we say antique, antiquity, for back then, at the time of the Roman, and they use this low tech device to find masses, and you will have to calibrate. Um, okay, it's a lot of fun. I think I will keep that for. So, for example, if I have uh, 5, okay, so 5 times 3 is 15. So 15, I can place it here, and you see it's gonna be, no. Oh, I didn't put at 1, right? 1. Now it's gonna be balanced. Okay. It's a seesaw, right? And then you can do it, try. So somewhere there. Okay, you can play with it. Okay, so that means this distance plus that times that plus this distance times that equals this distance times this plus that times that. But except it should be in between, but I can't. But you get the idea. It's fun. Yeah. Miss something here. Because torque is the force times the distance. The force, okay, I see what you mean. The force is the weight in that case. It's the weight. And the weight is mass times g. So the force here is the weight, which is mass times g. And because it's an equilibrium, you have a g here and I have a g there. So you can keep in kilograms instead of going Newton. It's like a unit, right? Newton is proportional to kilogram. You multiply by 10, you get Newton. So it doesn't matter. You cross out the g on both sides, right? So the force is the weight, and the weight is proportional to the mass. Okay? So just a tangent for those who are interested. I mean, it's interesting. Interesting. All the muscular system is all machines, right? You have pulleys, you have wheel and axle, and you have levers, and it includes the muscle, the tendon, the bones, the joint. You know, all that. It's called biomechanics. So you have levers. So levers, you have 3 types of lever. You have class 1. Class 1, it can amplify the distance or amplify the load. So you have the effort, the axis of rotation, and the load. So if you do it this way, it's going to amplify the load and the effort. And then you have class 2. Class 2 always amplify the effort. It will make you stronger. So in that case, the axis of rotation is here. The load is between the fulcrum and the effort. Lever 2. Lever 2, look. I don't have a small mass, okay? I have a big mass, but look, I can lift myself. Isn't that amazing? I can lift myself because this torque here about the toe is amplifying my force, right? My muscles. Okay, I'm amplifying the force. I apply a torque, right? I cannot lift myself very far, but I can do it. I can lift 80 kilogram, which is 160 pound. I will not be able to lift 160 pound. No way. But here I can do it. Isn't that amazing when you think about it? 80 kilogram, 160 pound, right? 160 pound. Not even on the bench I can do that, right? It's huge. Okay, so that lever type 2 will amplify the effort. Type 3 always amplify the distance. Okay, so in that case you have the fulcrum, the effort is between the load and the effort. So here my arm, right? My arm, the muscle here is attached to here. This is the axis of rotation and that's your load. The muscle is attached here. You see the effort is between the axis of rotation and the load. You're amplifying the distance, so there is a price to pay. You cannot curl that many weight. You cannot curl that many weight because because it's not designed for that. It's designed for distance amplification. That's why the bone here is very easy to break. It has a very small weight because it's not designed to lift, to curl that much. Okay, so example, level 1, amplify distance, amplify effort. Level 2, amplify effort. Level 3, always amplify distance. Okay, you with me? Isn't that interesting? So cool. Okay, so level 3, always amplifying distance. You amplify the distance. You have wheel and axle on the same principle. So for example, here you can apply a small force over a large distance will be equals to a large force over a small distance. So you're amplifying the force. Mechanical advantage will be large. This is called wheel and axle. You have that in the human body. It's all machine, right? In the human body, if you do oh yes, if you do something like this here, if you do something like this here, it means small rotation here. So in that case, you are amplifying the distance. Small rotation here, big rotation there. Small rotation, large muscle here, small force there. So that will be wheel and axle. This is wheel and axle. So here you are amplifying the effort, right? Large distance, small force, small distance, large force. So you can lift a heavy load. And here, wheel and axis, right? Guess when you do this. So it depends. What's the input? What's the output? If this is the input, you amplify the distance. If this is the output, you amplify the force. Okay? Gears, same idea. Low gear, you amplify the so that will be small, so large angle, small angle, you amplify the torque. You amplify your force, that will be to go up slope. If you do the opposite, then you amplify the speed. Gears, same idea. Pulleys, machine too. Okay, so let's do this one. It's a static equilibrium. We want to take the axis of rotation at the shoulder joint here. You have two forces acting from the shoulder. Okay, but if we are using torques, the torque applied by those forces here at the shoulder joint will be equals to 0. Because if you apply a force at the joint, you are not making it twist, right? If I have the wheel, if I pull here like this, nothing happens. If I apply here, nothing happens. So the torque applied by those forces that comes from the joint is not. So all this, it's important for in engineering, I guess. Dumbbell. So first of all, you choose the first thing you want to do is to choose your axis of rotation here. Boom, 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 boom. And I don't know, you see here you have a muscle. That's a deltoid muscle. Okay. The angle is 13 degrees. And then here you have the mass, the weight of your arm. And here you have your load. This is your load. Okay, so this one wants to do clockwise. This one wants to do clockwise. About here, this one wants to do counterclockwise. It's pulling this way. Are you doing it? I didn't lose anyone. So you go from the tail to the head. So we want to find the perpendicular, okay? Perpendicular. So you see your muscles, it's not because you have 1840 Newton muscle that you can lift 1840 load. That's because you have an angle here, right? Okay, so do it. So the sum of all the clockwise torque equals the sum of all the counterclockwise torque. So clockwise will be load. The load, I don't know how to call it. The load, L, load, times the distance, right? So 0.620 plus this, no, this, which is the weight of your arm, which is 31 times 0.280 equals this. 1840, you have a sign, and the distance is 0.50. Okay? So Newton on one side, Newton on the other side is fine. Meters on one side, meters on the other side, it's fine. You can use centimeters. Anyone? We're good? The first thing you have to decide, and I should say that the torque applied by these forces from the joint, right? The shoulder, you push on the shoulder is pushing on you. This torque here will be equals to 0 relative to the axis of rotation, right? So if you apply a force at the axis of rotation, if you push on the hinge of the door will not open. So you should find 86 Newton. Yes? So 86 Newton is about 90 Newton. 90 Newton is about 9 kilogram. 9 kilogram is about 20 pounds. So 20 pounds, it makes sense, right? 20 pounds. Okay, let's try to do this one. So do it. We do have class Tuesday, you know that, right? There is no class Wednesday, but there is class Tuesday. Mm. So 2.5, that will be 30 centimeter. Okay, so let's take the axis of rotation here. So that will be my fulcrum. 8 kilograms. So here I have to convert to Newton. I don't have to worry about the centimeters, but I want Newton. So that will be 80, and he has 3 kilogram here. So here you have 30 Newton. That distance is 12. Everyone? So that will be clockwise, counterclockwise. So the sum of the counterclockwise equals the sum of clockwise. So the muscle times 2.5 equals 80 times 30 plus 30 times 12. Okay? And you get something like this. Yes? Did I get it right? Yes? Okay, so 1,000 Newton, that will be about 100 kilogram. That will be 200 pound. Is that possible? Is that possible? No. It's not possible, right? 200 pound with one hand. Yeah, not possible. Is it? Oh, the muscle. Oh, yes, yes, you're right. So it's a muscle 200 pound. So, yes, so I guess, yes, you're right. It's possible. 200 pound. Imagine that. We can provide 200 pound. Yeah, yeah. No, I thought it was no, the load is 20 pound. So the muscle is 200 pound. Oh my God, 200 pounds. Okay, so this is very important because that's on the final. Let's see, a lot of application. So for example, which one will win easier to win? The short or the big? The long one. The long one, right? Because about the axis of rotation, the distance is larger, so it will be easier. I mean, the torque will be larger, right? So it does matter. This morning I learned that you have two kind of bicep. Did you know that you have a short bicep? You know that? And long bicep. I didn't know that. Apparently it's genetic. So close the parenthesis. Where is my student? Torch. Oh, that was one of my students back then, an athlete. So he did a demo. I didn't tell him to do the demo. He came up with this idea to show torques. So axis of rotation, that will be the effort, that's easy. And now the same force, he has to use his own weight and he cannot even move it. So the distance from the axis of rotation matters, right? So if you decrease the distance, you decrease the torque. Okay, so the torque is proportional to the distance. Here also, same idea, that will be the resistance that your fulcrum, that's the effort. So larger is the distance here, easier it gets. I'm gonna start doing this one. So the first thing you want to do, so it's typical for civil engineering, and you have one like this for the final. Can you do like not the free body diagram, but can you draw the forces acting on the system? And the system is the beam. Remember, in physics, you want to focus on the system, and the system will be the beam. Okay, what it's called? Like that thing here. Okay, don't stare at me. Don't stare at the screen. Do it, do it, do it, do it. So draw all the forces that you can think about. So you place the beam inside the bag. Okay, so that will be your system. You want to find what will be the force acting on it. So first of all, you can have the tension here. Agree? Okay, boom, 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 boom. Oh, you have a store sign. Okay, so here at that location here, you have a weight, which is 200 Newton. So you neglect the mass of the beam because they don't talk about. But not only that, here it's attached to the wall. So the wall is going to push back because pushing on the wall is going to push back, and it doesn't slide. So that means you also have some static friction. Now, in mechanical engineering classes or civil engineering, they will do that. They will say, okay, it's like you have another force here, and they call that force R. So they take those two forces and they say, oh, this is a component. These are component of a force, and they call that force R. Because it's a reaction from the wall. You have some static friction, it doesn't slide, and you push, and it's going to push back. Now, the trick is to take the axis of rotation to get rid of as many forces as you can. So I'm going to take the axis of rotation here. So that way the torque applied by that force relative to the axis of rotation is going to be 0. The torque applied by the normal force, it's going to be 0. Agree? Because you push on the axis of rotation, so it cannot make it twist. Okay, so that will be static equilibrium. That's how you want to do it. So that will be clockwise. And here you can find the component. So it has two components. The perpendicular component is doing the job, right? And this one is just pushing into the wall, pushing into the wall. Okay, so if I don't finish for next time, because that's reviewing for the final. You always have one problem like this. This one is doing counterclockwise. So the sum of the counterclockwise will be equals to the sum of the clockwise. Yes? So counterclockwise, it's going to be the sine. So it's going to be t sine 25 times the distance, which is 3, equals clockwise will be the 200 times 1.5. 237. Okay? And then they might ask you, can you find the normal force? Can you find this force here? So then I will use everything right equals everything left. So the normal force is pushing to the right. So I will say normal force equals this component. You see, this component has a different job. Its job is to push on the wall. You need to push on the wall, otherwise you don't have static friction, right? So it's pushing on the wall. And that will be T, which is 237. And that will be a cosine 25. Agree? And then you have everything up equals everything down. So you will have this component here, which is T sine 25 up plus the static friction equals 200. And you can find the static friction. And then your civil engineering class will say, no, 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 we don't like that. We want to find R. We want to find the magnitude of R. So in that case, you will do the magnitude of R will be square root exactly normal. So they will do that in engineering. But otherwise, that's on the final. You have one like this. Any question? If you have any question, let